One of the more prominent analysis types in sigma W is what we call a load deformation type of an analysis. In this session, we're also going to talk about the concept of incremental loading and the implication of an incremental formulation in sigma W. We're going to illustrate these concepts by doing a footing analysis. It is rather a curious example because we never build footings on the ground surface. However, this type of an example exists in all textbooks, and as a result, everybody is very familiar with the Boussinesq pressure bulb beneath a footing, and consequently we have an appreciation before the analysis as what the stress distribution should look like after we apply our footing pressure. What I'd like you to notice in this slide is that we have here a circular footing, and we have the diameter of the footing is B, and we have contours here of the percentage change of the applied pressure. So when we are at a depth of 1B, this graph says that we should get a pressure change of approximately 30%. Keep this number in mind. So we are looking at a depth of 1B. We should have a pressure change of approximately 30% of the applied pressure. Here is a sketch of the sigma W problem. We are going to analyze the case of a round tank. The tank is going to have a diameter of 10 meters. It's a very large oil tank, for example. And we are going to do an axisymmetric analysis and apply a tank pressure of 100 kPa. Now, sigma W can handle an axisymmetric analysis in that what we are really doing is a three-dimensional analysis, but the finite element mesh is a 2D mesh. However, we are doing a 3D type of analysis. It is important when you select an axisymmetric type of an analysis that the central symmetric axis must be at x equal to 0. We will demonstrate how to select the load deformation type of analysis. We're going to select a load deformation type of analysis, and then in the set units and scale, we're going to select an axisymmetric type of an analysis. So the exercise to illustrate the procedure is in file SIG02. And first of all, to start with, we are going to imagine that we are simulating a tank with a flexible base. It's a flexible base. It's like a flexible footing. We will apply a boundary condition on the left side, right side, and bottom of the domain, and then create a boundary condition representing the tank pressure and apply this boundary condition. And then we want to make contour plots of the vertical stress to create a pressure bulb and graph the surface deflection and the lateral deflection on the edge of the footing. Going then to GeoStudio, open up file SIG02 round footing. Part of the problem has already been set up to save time here. We can click on our Zoom Objects button, and I would like to look at a higher zoom than what that gives me, say 100%. Turn off Snap to Grid, but remember that we are doing an axisymmetric type of analysis. First of all then, under Set, Units and Scale, notice that we have selected axisymmetric. And this brings up a point, is that once you have a file with an axisymmetric analysis, all analyses in this file must be axisymmetric. You cannot mix and match two-dimensional and axisymmetric problems in the same file. This is, so to speak, a global parameter that must apply to all analysis in this file. So we have selected an axisymmetric analysis type. Under Key in Analyses, notice that we have selected a low deformation type of analysis. And in this particular case here, notice that we have not selected any initial stress conditions, and we have not selected any initial pore water pressure conditions. We are going to ignore the pore pressures in this particular illustration here. To begin with then, a material has already been defined. Key in Materials, the foundation soil. Notice that we have selected a total stress parameters here. This is because we can use this material category because we do not want to say anything about pore water pressures. It's a linear elastic type of model, and we have assigned the total Young's modulus to the soil of 4,000 kPa. Now, it's incredibly important to recognize that we have not given the soil any unit weight. The reason is because we do not want to consider the self-weight of the soil. We want to look only at stress changes, not the self-weight of the soil, and an arbitrary Poisson's ratio of 0.45 has been used in this particular case. So the material has been defined. Then we say Draw Materials and assign this material to the domain. We need to define our boundary conditions now. Say Draw Boundary Conditions. We want to fix the base of the domain and fix the right-hand side in both the XY directions. On the left side, we want to allow movement in the vertical direction, but not in the horizontal direction. So we fix it in the horizontal direction, but allow it to move in the vertical direction. Now we need to apply the tank pressure, saying Draw Boundary Conditions. Key in. We have a boundary condition here, and it is an X stress type of boundary condition. I could have selected a normal type, but I want to illustrate a certain thing here, and that we have a XY stress, and we are specifying the stress in the Y direction, and because it is downward, it is a negative 100 kPa. Repeating then, because it's an XY stress, we have to assign to the stress depending on the direction of the applied stress. So in this particular case, we are specifying the stress downwards, which is represented by a negative value. So we are applying minus 100 kPa. Draw, and assigning it to a line, we can assign this boundary condition to the line under the tank footing. Now notice that there's a note here that says element thickness is 1 radian. If we look at our finite element mesh, there are several features noteworthy here. Draw mesh properties. The global mesh size is approximately 1 meter, but if we select the region, notice under elements we are using secondary nodes, higher order elements, but the element thickness is 1. This means that the element thickness is 1 radian because it is an axisymmetric type of analysis. If we were to enter here 2 pi radians, we would get the total circumferential distance around the symmetric axis, but in this particular case, analyzing it as 1 radian thickness is a more than adequate. Notice also that I have used some constraints on the mesh, and that on the right-hand side, I've said that the default ratio, in other words, the elements are twice the default of 1 meter, so that I get larger elements. Same thing on the bottom boundary. Once again, the length is a ratio of the default size, and I said that the elements could be 2 times the global size. In this way, you get a mesh with finer elements underneath the footing and larger elements away from the footing. Turning off the grid then, we don't need to look at it any further. Notice here then that we are in this particular case at a unit thickness of the elements, but in this case it represents 1 radian. And notice that the symmetric axis is where x is 0. Clicking on our Verify Optimization icon, we see that we have 0 errors, 0 warnings, meaning that we have supplied sufficient information to make calculations. Clicking on the Solve button, we can now solve this problem. Clicking on the Start button and going to the Results view, we see that the vertical stress contours have been plotted here. We are plotting the stress contours starting at 10 kPa. Notice the auto range has been unselected, so we are starting at 10, incrementing by 10 with 10 contours, meaning the ending contour should be 100 kPa. What we now have shown here is a pressure bulb, as we expected from the illustration from a textbook. And notice now that when we zoom in here, we said that from the pressure bulb published in the textbook that we should get 30% at approximately 1D. And indeed, sigma W, the contour of 30% change in stress, is very close to 1B. Now you will find that as you get closer to the perimeter of the domain, for example, if you get closer to the base here, the 10% contour is not going to exactly match what you saw in the textbook chart, but we could get it more close by having a larger domain. But the point here is that we have done a load deformation analysis. We applied a surface pressure, but what we have computed here is the change in stress. And what we have computed is a pressure bulb which represents the stress change in the ground. It is not the actual stress in the ground, as we will see in a moment. Now, the exercise called that we were to plot, make a graph of the settlement. We are looking at the settlement over this distance here from the center line, symmetric line, some distance past the edge of the tank, and we see that we have settlement here, a settlement profile, something like this. The edge of the footing is at 5 meters. So here's the edge of the footing, and here is the settlement outside the footing. Here's the settlement under the footing. Also, another interesting graph is the lateral deflection on the edge of the footing. We'll select a geometry location, which is along this line here. Show the graph. So here we see the lateral deflection under the footing at this edge of the footing. And we see that a short distance under the footing, the soil gets squeezed to the side a lot, but then the amount of squeezing to the side diminishes with depth in the profile. So the primary purpose here has been to illustrate the idea of an axisymmetric analysis and to apply a surface pressure and to draw your attention to the fact that these are changes in stress. They're not the actual stresses in the ground. We'll continue the exercise now by looking at another type of boundary condition, and this is very common in numerical analysis, that we simulate certain features with a boundary condition. In this case, we can simulate the effect of a rigid footing with a specified displacement boundary condition, say 50 millimeters or 0.05 meters. So what we're going to do is clone the first analysis and then apply our displacement boundary condition and again look at the results. Going to GeoStudio, key in analyses. We will clone the first analysis, call it number 2. Specified displacement. Everything else is the same. Going then to key in boundary conditions. We want to add a new boundary type, and this will be specified displacement. We are a specified displacement here, and we want to specify either force or displacement type of boundary condition, and we want to specify a Y type, and in this case it's Y displacement, and once again it's down, so we have to say minus 0.05 meters of displacement, giving it a different color, say a green color. close, we can then say draw boundary conditions and apply our displacement representing a rigid footing. Now in this case it is not a rigid footing, but imagining the tank were to sit on a very stiff concrete slab, it might look like a stiff footing, and the point here is to illustrate that a stiff footing could be specified with a boundary condition. Once again, it appears that we have all the information we need to make some calculations. Clicking on Solve, saving the problem, running the analysis, going to the results view. We see that the pressure distribution, the change in pressure, is quite a bit different. In this case, let's turn on auto range, and we see that we have quite a different stress distribution in this particular case. But that is not what I want to draw your attention to. What I want to draw your attention to is to the settlement profile. We say draw a graph and settlement. So in this case we are plotting displacements, y displacements versus the horizontal distance for our tank load specified displacement analysis, and we now see that we have a constant 0.05 meters of displacement under the footing. Then outside the footing, of course, we have some variation in displacement, and a long ways away from the footing the displacement is very small. Since the displacement is the same everywhere, we have in essence simulated the effect of a rigid footing. Now, this leads us up to the next topic in a little bit. It's not so dramatic in it itself here, but what we have done is illustrated the application of a surface pressure, and we have shown how to apply a specified displacement as a boundary condition. The basic finite element equation for sigma W reduces down to this very simple equation here, where K is the system stiffness or characteristic matrix. It includes the material properties such as E and Poisson's ratio and volume or area. D is a vector of nodal displacements, and it is also known as the primary unknowns that need to be computed. And F is a forcing vector or a vector of nodal action forces. And to those of you who have been part of other sessions like the CW session will already recognize the form of this equation is essentially the same in all finite element analyses. However, in this case, in sigma W, it is more correct that the finite element equation is equal to K times some incremental deformation is equal to an incremental force. And this is what we mean when we say that sigma W is based on an incremental formulation. We have just shown that we applied a surface pressure, that we got the change in stress in the ground. We didn't get the actual stress in the ground. And that is because sigma is based on an incremental formulation. This means that an applied load gives the change in stress as we have just talked about. It means a change in stress. The applied load creates a strain increment, which in turn creates a stress increment. So what we are computing is a strain increment which leads to a stress increment. In sigma w, the change in stress always comes from the solution to the finite element equation. The change in stress is added to the initial conditions. If we do not define the initial conditions, then we only get the change in stress. So in our footing analysis so far, we did not define initial in situ conditions, and therefore we only got in our analysis the change in stress. Stated another way, the stress equation looks like this in sigma w. The finite element equation and the finite element solution always produces the change, and then we add it to some initial or previous condition to get the actual stress in the ground. To repeat, it is very important to recognize that sigma w always computes the change in the stress, and that changes get added to the initial conditions. So returning back to our diagram here, this is a pressure bulb, and the pressure bulb only represents the change in stress. It is not the actual stress in the ground. To illustrate further the incremental formulation, what we are now going to do is we are going to apply a specified displacement 5 times. Each analysis will have a displacement of 0.01 meters per increment, and then we will do 5 steps and see how the increments accumulate to give us the total in the end. Returning to GeoStudio, returning to the define view, key in analyses, let us clone our displacement analysis, calling it analysis number 3. And we will do 5 load steps. So we now have a third analysis. And in this case, we need to say that we want to do 5 analyses. So we need to select the time tab here. We select the time tab. Now it is not real time. The real time comes when we do a coupled analysis, but in this case you can think of it as load steps instead of time. So in this case we will have a duration of 5 and we will have 5 steps. And so we have seconds here, but we can ignore the units because they are meaningless. What it is really saying is we are going to do 5 steps, one after the other. So you notice that we are now doing 5 load steps, and we will see how the displacement accumulates as we run the 5 steps. We need to now create a new boundary condition, draw boundary conditions, go to the key in boundary conditions. We will clone the specified displacement and say this is incremental displacement. And the incremental displacement will be 0.01 meters. And we will select a different color to readily distinguish that we have applied a different boundary condition. Close our key in boundary condition. Now we can draw this displacement representing the displacement of the footing. Clicking on Solve, saving the problem, rerunning our third analysis, I will uncheck this box here such that our Solve window will remain open, and we can see that we are doing 5 different analyses. Click on Start. And now notice that we have done 1, 2, 3, 4, 5 different analyses. In each analysis, we applied a displacement of 0.01 meters. Going to the results view, draw a graph. We plot the settlement for number load step 1. If I hold down the control key, I look at the settlement for analysis 2, analysis 3, analysis 4, and analysis 5. So in each analysis we have had an increment of 0.01 meters. So 0.01, 0.02, 0.03, 0.04, 0.05. Now, the whole point of the exercise is to introduce you to the concept of an incremental analysis. And when we do incremental analysis and we do many different steps, then the results accumulate with the analysis. But during one analysis, what we are doing is applying either an incremental load or an incremental displacement. This brings us to the end of this session on a load deformation type of analysis, where we have done an incremental stress analysis. We have applied a stress boundary condition, a displacement boundary condition, but most importantly of all, this session has introduced you to the concept of an incremental analysis. And it has to be very clear in your mind when you are using sigma W that each load step produces an increment and the increments get added up together.